All right, so here's how we get into a two-dimensional relative velocity problem. We have Raphael in his boat, and let's say that the water is flowing down at some velocity relative to the ground. So that means if you're on the ground watching, you see the water flowing. So this is velocity, water, ground. And what we want is Raphael wants to have his boat go straight across so that when you're standing on the ground, so maybe this is like you standing down here and you're looking off that way, he wants to go straight so that you would see him coming straight at you. So that's going to be the velocity boat ground. The question is, maybe what angle does Raphael need to go, and maybe what would his velocity be? So the thing that we know is that his boat in the water, he's got to aim it this way. He's going to aim it upstream, velocity boat water. And then we can find out what angle upstream he needs to go. So let's say that we know that velocity boat water. Raphael knows that his boat can go 4 meters per second. And that the water, velocity water ground, is going at 3 meters per second. And we will, again, what do we want to know? We want to know what angle, and we want to know what is the velocity of Raphael's boat measured by the ground. So now, again, we can use subscripts to help us out here. And we can say that velocity boat ground is equal to velocity boat, we start with what we started, plus velocity ground. We end with what we ended. And what's going to be our link? It's going to be water. Water is the thing that we know with this. So velocity boat water, well, that is this 4 meters per second. And we know that velocity water ground is 3 meters per second. You might say, that's 7. But 7 is not the right answer, because since we're adding these as vectors, we have to actually look at the right triangle. So what we're saying is that we have velocity boat water going like this, plus velocity water ground like this, is going to result in velocity boat ground pointing straight down. So we actually have to use Pythagorean theorem. So we do, this is 3 and 4. But what we need is not the hypotenuse, and that's what makes this difficult. Our equation helps us get our sides in place, but we've got to look at our triangle to find out actually how we do this. So what I have here is I can say that velocity boat ground squared plus velocity water ground squared equals velocity boat water squared. Boat ground is what I don't know, so boat ground squared equals velocity boat water squared minus velocity water ground squared. So velocity boat ground squared equals boat water was my 4. So this is 4 squared, which is 16, minus water ground is 3, which is 9. So velocity boat ground squared is 5. Or then I take the square root of both sides, and I get velocity boat ground equals square root 5 meters per second. Now we need to find out what this angle is. To do that, we've got all our sides But I'm going to use the sides that I was given. So we had boat water, which is hypotenuse, and we have water ground, which is opposite. And I know that sine of theta equals opposite over hypotenuse. So sine theta equals, water ground was 3 over boat water, hypotenuse is 4. So I have sine theta equals 0.75. But again, I don't want sine theta. I need to undo that. So I need to do the inverse sine of this side, which knocks out sine and leaves theta. But I need to do inverse sine of this side. So theta is the inverse sine of 0.75. So that leaves us with theta equals, and that's 48.6 degrees. So what does that mean? If Raphael aims his boat 48.6 degrees upstream, then the current's going to push him downstream. And while all that happens, his boat's going to be angled off, but his boat's going to come straight across the stream, and it's going to be traveling at root 5 meters per second.